Hi everybody. Today we're going to start off by talking about chemistry. Now you might wonder, why are we going to talk about chemistry in a biology class? Well, the thing is that you are basically a giant bundle of chemical reactions. You're made up of atoms and molecules, and they're interacting with each other constantly so that you can function. So it's really important that we understand the basics of chemistry in order to understand how you function. Now, I've had many students over the years who come to me at the beginning of the semester and tell me, I've struggled in A&P before, and I just need to get through chemistry and I'll be okay. Well, technically they're correct. If they just get through chemistry, they'll be okay. The problem is that's going to be about, for this class, 7.5 or 15 weeks from now. So in other words, the end of the semester. Chemistry is embedded in every aspect of this course. Now, before you get stressed out, let me just say up front, I should have a sign on my forehead that says, not a chemist. I'm a biologist. I'm going to approach this from a biology perspective. If you've had chemistry in the past, you're going to find probably that what I'm talking about is going to be really superficial compared to how you learn things in a chemistry class. If you have not had any chemistry before, don't worry, I'm going to cover what you need to know. And you can just rewatch the video as many times as you need to until it kind of sinks in. So, why do we need chemistry in here? Because you are made of chemicals. And when those chemicals interact with each other and build things and break things down and stuff is happening, well, we've talked about this before, that's good old physiology. So to understand the physiology of the body, we need to understand the chemistry. So we're going to go back to the bare bones basics here. So first of all, elements. What's an element? Well, an element is composed of small substances called atoms, and all of the atoms within an element have basically the same properties, right? They're kind of built the same. If we look at living organisms like you and me and a dog and a tree and a worm, all of those organisms have something in common. About 96% of those living organisms are made up of just 4 elements. That's it, 4 elements. Oxygen, carbon, hydrogen, and nitrogen. Now there are a few others that are particularly important for our bodies to function, and we'll talk more about those in a little bit. But these are the big 4. So to understand what elements are and what we need to know about them, we're going to look at something called the periodic table. I'm not even going to worry that I'm covering up the bottom here because these are all molecules and elements that are not going to be particularly relevant to our bodies. So when I look at the periodic table, these are all of the elements that have been discovered, so far anyway, and there are some here that are particularly important for how your body functions. So I'm going to go through and kind of circle those. So we have here H, so that's hydrogen. Na is sodium, magnesium, potassium. Now if it seems like some of these, like sodium and potassium and others, the name doesn't match the symbol that you see, the letter in the middle of the box, then that's usually because there's some Latin or other kind of root word or term for that element. Ca is calcium. You know that's important. We kind of cruise along over here. Fe is iron. Zinc is a trace element. You do need some of it, but only in very, very small amounts. We're not really going to get into that. Carbon, probably the most important element in your body. We mentioned nitrogen and oxygen. Chloride. And I'll mention, let's see, one more down here, iodine. Now, certainly you have other elements in your body than these, but for these particular elements that I've circled, know their name, know their symbol, which is the letter or combination of letters in the middle. So we'll go over those just again real quick. We've got hydrogen, sodium, magnesium, potassium, calcium, iron, carbon, nitrogen, oxygen, chloride, and iodine. Now think about what you already know. What do you need oxygen for? Well, oxygen is important so that you can make a molecule called ATP. And if you've never heard of ATP before, ATP is very important. Think of it like the Duracell batteries in your cells that are just there to help run processes. So if you need energy right now to do anything, like taking notes, digesting food, whatever you're doing, you need ATP. You need all of these little batteries to run those processes. You need oxygen to make enough ATP for you to function. Carbon is really important because carbon is, as we're going to see later, sort of the perfect element for building things, because carbon needs to bond with 4 other things. So it's kind of like that perfect Lego piece that you can attach lots of stuff to. So you have lots and lots of those little kind of rectangular blocks in your Lego kit because they're the perfect piece to kind of fit lots of other things around. Iodine is important for making the hormones that are produced by your thyroid that regulate your metabolism. Iron is found in red blood cells and is necessary for carrying oxygen. So in other words, we need iron, again, to make ATP, because we need the iron to carry the oxygen so that we can make that ATP. Hydrogen, I like to think of it as like the perfect spackle, so you can use it to fill all the holes in molecules. We'll talk about that in a little bit. Sodium tends to get a bad rap. It can be bad for you. It can raise blood pressure and things like that. But sodium is necessary. You need sodium for neurons to fire. You also need potassium for neurons to fire. You also need potassium for muscle contractions. Calcium, go back here. Calcium, most people, when they think of calcium, they think of bones, right? So we think of calcium, we think of bone strength. And yes, it's important for strong bones. However, it is more important for your body that you have enough calcium in your bloodstream than you have enough calcium in your bones. And the reason for that is that we need calcium for muscle contraction. In fact, it kind of gets the ball rolling and gets the muscle starting to contract. And we need it for neuron communication. So neurons can send signals to each other, things that we call neurotransmitters. So know those major elements, and then we'll talk about next how you interpret what's actually in the periodic table. So let's take one of these boxes, for example, here. So let's take carbon, since we said it's such an important building block. Let's take an atom of carbon and see what we can tell from our periodic table information here. So if I looked at that box on the periodic table, I had my symbol in the middle, and then I had a number down here. In this case it was 12.01, and I had a number up here which was a 6. Now don't worry, I'm never going to ask you to memorize the periodic table, but if I give you the information from the table, you should be able to interpret what that means for that atom. So we said this is my symbol. This number up here, that's a whole digit, is my atomic number. And the number down here is my mass number. Now my atomic number is going to tell me the number of protons in that atom. So if we think about an atom, there are 3 subatomic particles. We've got protons, neutrons, and electrons. Proton is in the nucleus of the atom. It It has a +1 charge, and it has a mass of 1 atomic mass unit, so it weighs 1. Neutrons are also found in the nucleus. They do have no charge, so they are neutral, electrically neutral, but they also have a mass of 1 atomic mass unit. Electrons are kind of like those little satellites that are orbiting around Earth. The protons and neutrons make up Earth, and my electrons are the satellites. So they are orbiting around the nucleus. They are in orbitals around the nucleus. They have a -1 charge, and they weigh approximately 0. Now they do have mass, but their mass is so tiny compared to those protons and neutrons, it's effectively 0. And if you think about that, that makes sense with my planet. It's really heavy, has a lot of mass. And then those little satellites that are orbiting around the planet don't really have much mass compared to that overall planet. So back up here, my atomic number, these are my numbers of protons. Now that can never change. So every atom of carbon out there has 6 protons in its nucleus, all of them. The mass is going to be approximately the number of protons plus the number of neutrons. Because if you think about it, electrons don't have much mass, and each of these does. Now, it's not perfect. There's a difference between mass number and atomic mass. If you want to know the difference and get into the details, you're going to have to take a chemistry class. Because remember, not a chemist. We're going to keep this really simple. What we know then, though, is that if I have 6 protons in an atom of carbon and a mass of 12, well, 12 minus 6 means there's definitely some other stuff in that nucleus, so there are definitely some neutrons in there. I'm not going to ask you to calculate how many neutrons are in an atom because, again, that gets into some specifics that you would learn in a chemistry class that get pretty detailed. So we're going to focus on the fact that if this number is bigger than this number, we know there are neutrons in there. Okay? So what are we missing? Well, we're missing electrons. The number of electrons will equal the number of protons if my atom is neutral. So now this is going to have to be a little bit of a trust thing here. Without getting into too much detail about the origins of atoms and things and, Big Bang Theory and so on, just understand that all atoms start electrically neutral. Okay? So all atoms start electrically neutral, which means in a neutral atom of carbon, my atomic number is also going to give me the number of electrons, right? Because the number of pluses has to equal the number of minuses, because these are positively charged and these are negatively charged. So my atomic number gives me the number of electrons in a neutral atom. And unless I tell you otherwise, you're going to assume that my atom is neutral. Okay? So what I want you to do before you watch the next video is I want you to pick at least a couple of the other atoms or elements that I circled on the periodic table. So we'll go back here. Pick 2 or 3 of these elements, and using the information in that box, I want you to determine the number of protons, the number of electrons, and whether or not you would find neutrons in there.